Hey kids, today we're going to be talking about something that is near and dear to my heart. British Leyland. Wait, no. Codswallop, RPL. This is a language that I've been working on for some time now. So what is RPL? What does that mean? Well, it means Reverse Polish Lisp. It's a language that Hewlett-Packard came up with for their ultra fancy calculators in the late 80s, early 90s. It is a sort of bastard child of Forte and Lisp in that it is a stack language. It runs a lot like Forte, but it has a ton of data types, kind of like Lisp. So what I'm going to show you now is this is fully interactive. So I'm just going to add 2 and 3. So 2, 3. You can see we have what appears to be a stack, a list of things that's growing as I type in numbers. Now that I have 2 and 3 on the stack, I can say plus, and now these two numbers have disappeared, and we have 5. So that is the basic way. Instead of having a line that says, you know, x equals 2 plus 3, what you would instead have is 2 and 3. That puts 2 and 3 on the stack, and add. So that's how we got what we have there. Then we can say the symbol x, and we can store it to x. Now the stack is empty, but x is there, and if we show it unquoted, it'll come right back. That's what we put in there. So that's basic addition, and you can see that we were able to put both a number and a symbol on the stack. There are in fact a whole bunch of data types, and it's fairly trivial to add more, but we can go through a couple of the useful ones here. You have an integer and a float, so we were working with floating point numbers just then. Functions and symbols, that's quoted and unquoted symbols like that. You can have regular strings. You can have comments, which are kind of like strings, but they disappear instead of ending up on the stack. So if we said, this is a comment, then the language will evaluate this comment, but because the evaluation doesn't do anything, it doesn't push it to the stack, it just disappears. Whereas a string will end up on the stack. Now, let's see. It's also worth noting that code is a data type. That means that any old block of code, you can interact with that just like you would interact with any other sort of data type. HP called it object-oriented, and that's kind of true in that all of these things are objects, but it's not like a Python object or something like that exactly. So you can also have a list. So you can be like 1, 2, 3, 4, 5, and that's a list of 5 things. You can have a list can be anything. It's just a collection of objects. So it can be like hello, symbol, unquoted symbol, a integer 5, a number 5.0, and like, oh, another symbol, and a comment. This is another comment. And you can see the way this works, we've got full highlighting of the different object types, so you can kind of see what you're doing. We will clear out the stack. So all of your interaction is done by, you put arguments on the stack, then you evaluate a symbol, which will maybe do something to it. It'll run a piece of code. Maybe the code will pull things off the stack, and so all of the arguments come off the stack. All of the results get pushed back onto the stack. So there's only one way to interact with anything. It's going to do its thing. And it all comes into and out of the stack. That means that that it's a lot more simple in terms of the grammar, because it's just going to be a list of objects. So if I wanted to have a program that said, give me a number, and then I will put it in X, then you can just say, you can make a code object that says, give me a number and put it in X. Well, and I will put it in X. And then we'll ask for a number, and then we will turn that into a number, so to float. So we put this on the stack, prompt takes it, asks for information, and whatever you type in goes back onto the stack. Float takes what you typed that's now on the stack, turns it into a number. Then we put X on the stack, the symbol, and store takes our float and our symbol and stores that into the main store. So now we've got a program. We can put that program into a thing, so we can type useless, and now if we run useless, then it prompts us. We can put in a number. We can be like 3.35, and now we don't know what it's done, but if we recall, then it's stored that to X. So we can also manipulate this program just like we would with a list. That means you can take elements out of it, you can move it around, you can take part of it. Like if you just wanted the X store, you could be like useless recall, and let's say we wanted to write 2 elements out of that. We would say write 2, and now we've got a subset of that program. And this is all different to Algol. And Algol-derived languages, which is like everything you've ever used, unless it's some kooky weird shit like Haskell or OCaml or whatever. So it's a little hairy to write, and that's partly because the Algol-derived languages don't let you just randomly leave anonymous data on the stack for use in a later time. So you do have to like keep more of the machine state in your head as you're writing this stuff. But you've noticed I could have typed these in one at a time and just pressed enter after every single object, and it would have run this program step by step. And that means it's very interactive. You can feel this stuff out, and and that's based on the fact that it was a calculator language. It was meant for you to sit and talk to the machine, as opposed to coming up with some elaborate script and then hoping the machine runs it correctly. So I have in my notes here that I should shit talk Algol, and that's not exactly true. The limitations do make the programs easier to read. Whereas, like, some of the RPL stuff is like, I go look back and look at the stuff that I've written, like, I don't know what that does. But there are some important self-documenting features of this. So if I just type question mark, then we get a list of all of the names in the named store, which are highlighted by what type of object it is. So we've got a couple directories in here. All of these yellow ones are built-in commands. these white ones are strings, and these cyan ones are programs. The slightly dimmer cyan one is our number that we just put in. So yeah, the state retention, the fact that, you know, if you were trying to interact with Python and you were like, I want to know what 3 plus 5 is, then it would print the result back at you. But if you wanted to use that number, you would have had to store that in something. You'd have to be like x equals 3 plus 5, and then work with x from there. Whereas right now, this is all just like on the stack, and I could just continue to interact with it. I could move it around. I could add things to it, or multiply, or whatever. You can just keep doing stuff with your intermediate results. Also, these things have multiple dispatch. So if we look at how plus works, plus will do all sorts of stuff. And we can actually inquire as to what it will do. So by saying plus document, it says add or concatenate two objects, and then it says it's looking for two arguments, and it could be all sorts of different things. It could be an integer and an integer, it could be a float and a float, integer and a float, float and an integer, string and any and string, list and any, or you can add code together. So you can be like, this is part 1, this is part 2, and now we've got two programs, and now we've just merged it into one program. If you try to do something goofy that's not set up to work, then it'll complain about that. So you can be like, error. Let's add error to this. And it will say, alas, in object 0 of this program that we just ran. It would be like, there are 8 ways to call, and you tried number 9. And then it also leaves those arguments on the stack, so you know where it stopped, like what broke, and what state the machine was in when it broke. You can also do local variables. Those are done a little bit differently on this, but you can have a context. Let's say we want to have 3 in x, so x is 3.35 right now. But let's say we want x to be 3.7 for the purposes of this, and we'll have 3.7 on the stack, and we'll have our program that we want to run with the local variable, and be like, the value of x is currently, and then we'll say x plus, so that'll take x out of the store and add it to this string, and then we'll just say display. And so now that program's on the stack, and then we'll just make a list of local variables, which is just going to be the 1, and when I type local, it's going to run this program with this local variable that says 3.7, and it'll say x is 3.7. Now if we go back and run this program again without the local variable, then that's what it is, with the original value uncovered. There's a lot of self-hosting here, so like the REPL, the read evaluate print loop that we've been typing into right here, that is actually self-hosted. That's this program right here. We can actually recall it. And we can see this is the entire program on the stack, and we can, well, what we can see is that this camera will only do 15-minute chunks, which means I've been talking too long already because I wanted to do this in 10. But anyways, so the REPL here, it reads what you write on the prompt there, and it goes through. It tries to process it, parse it, and will attempt to, so it parses it right here, tries to run it right here, and then continues to loop until you're tired of talking to it. You can also use this thing called SST, single step. And if you're having trouble figuring out how one of your programs is broken, it's actually very helpful. You could say, like if this part didn't work here, you could put an SST right in here, and it would start single stepping from that point, and it would just evaluate one object at a time, and then it'll show you the machine state, like the state of the stack, with every single time you hit enter. So you can figure out what your program is doing down to a much more granular level than you could with, well, with most languages, to be honest. And that's pretty much that, except I wanted to show you that there is actual code that's written for this. So I, as part of developing this language, one of the things I wanted to do was write a program in it. And so I took the Wizard's Castle, which was actually it was an Exidy Sorcerer game that got ported to the PC in the very early 80s. And I converted it to RPL. So here I'm just loading it off the disk. And Wizard's Castle. It's a dungeon crawler it's a like Star Trek rules dungeon crawler. But it's a fun little game. And it works. And so obviously it's a very, very basic thing because, you know, it was a basic game. But if we look here, I have a whole bunch of code here, and you know, it all runs, and we can actually look at little parts of it, like look at L4030, which is trying to look at a spot on a map, or whatever, or trying to look at the entire map in the game. So yeah, there has been actual work that I've done in this, and I actually have it bound to a keystroke so I can play with it whenever I feel like, and it's, you know, I wouldn't write an operating system in it like some companies did, but it's really remarkable to have a language that you can just sit down and talk to the computer with interactively. You know, there's an interactive mode in Python, but it's really just to do the most rudimentary stuff, whereas you can really feel out pretty complicated stuff with RPL. So there's a lot more to talk about, but that's the basic overview. Good night.